Okay, I'm back. Number 7. A particular compound decays according to this equation, where T is in days. Find the half-life of this compound. Okay, so this is our formula for half-life. And so one thing you have to know about half-life is that, first of all, A is your initial amount. It's what you start with. And we're interested in the half-life, and that's what Y stands for. So we're interested in what half of this original amount is. So what is half of this original amount? I don't know, but it's going to be half of A. So this Y right here is going to get replaced with 1/2 A. Or if it makes it easier, you could do 0.5 A. And you guys might like that better. So I don't know what the original amount is, the initial amount is of this compound, but I know I'm interested in its half-life, so I want to know what half of this is. And so that's what Y stands for, is what we're looking for, half of it. So that's why we're going to replace Y with half A. So into the Y we put 0.5 A, and I recopy the other side. And that's what you're going to do every time you see a problem like this and it talks about half-life. All right, so since this A is multiplied with that, I can get rid of the A by dividing. And anything divided by itself is 1. So that makes 1, and that makes 1. So they're just gone. So all you're left with is 0.5 on the left, and E raised to the negative 0.0736 T on the other side. Okay, so we've already done this once today with the E as the base. So remember, whenever your exponent is a variable, you need to take the log of both sides to hop it down. So since my base is an E, I'm taking the natural log of both sides. So I'm taking the natural log of both sides. So the left-hand side will just stay natural log of 0.5. And on the right-hand side, this exponent gets to drop down in front now. So in front, I have a negative 0.0736 T. And behind it, I put natural log of E. But remember how natural log of E has a special value of 1? So if I put natural log of E back here, which is 1, 1 times this is just this. So the natural log of E basically just goes away. Okay, now this is very easy. To get T by itself, I need to get rid of these numbers, and since they're smushed, I'm going to divide. So I divide both sides by this negative 0.0736. So I divide both sides by negative 0.0736. Negative 0.0736. And then those would cancel out, leaving me just T. And the other side I put into my handy-dandy calculator. So remember, natural log is right here, ln. It's to the left of the 4. So natural log of 0.5, and then I'm just hitting the division symbol. I definitely could have done alpha y equals. So alpha y equals is great anytime you want to do a fraction, so you definitely could have done that. Since this wasn't too complicated of a fraction, I just decided to hit the divide button instead. And I'm dividing by negative 0.0736. And I get T to be approximately 9.4178. So this 7 rounds up because it has a 5 or higher behind it. And if I look at my answer choices, that is B. All right, so every time you see this half-life problem, just know that A is the original amount, and I want half of that. So we're going to replace Y with half A. And then you can divide both sides by A, and the A's just go away. And then from there, it's fairly easy. If your variable is an exponent, you take the log of both sides to drop it. Okay, next one. At a wholesale food distribution center, the price of sugar has increased 6.3% annually since 1980. Suppose sugar costs 43 cents per pound in 1980, and this growth continues. What will a pound of sugar cost in 2017? Okay, so A stands for our initial amount. So what was the initial cost of this sugar? The initial cost was 43 cents per pound in 1980. So 43 cents is our A. Okay, and then in parentheses, 1 plus, our rates are percent. So here's our percent, but I need to move that decimal twice to the left. So if I move it twice to the left, once, add a 0, twice, so it's 0.063. Let's close the parenthesis. And I want to know T, time. So this was the cost in 1980. I want to know what it costs in 2017. So how many years have gone by between 1980 and 2017? 37. Now, if you didn't know that, you could take 2017 and you could subtract 1980 and you could get 37. So that's my T. Okay, so now I just plug the whole right side in my calculator. So I've got 0.43 parenthesis, 1 plus 0.063, close it up, raise it to the power. So remember Mr. Caret above the division symbol. So raise it to the power of 37. And that makes this sugar cost about $4.12. We're back to money, so I rounded to the hundredths since it's money. And that is answer choice B, 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 B. No, A, 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 A. Hello. Get it together. Not you, me. That is answer choice A. Okay, number 9. This one, really easy. We're trying to write it in logarithmic form. So first, we write the word log. And then under the exponent is the base. So remember the base is always down low. This is the exponent, and it goes way out here. And what it equals goes in the middle. So I have a little song for this if you want to hear it. Some of you have already heard it from me personally, but if you haven't heard it, I'm going to sing it to you because maybe it might help. So because I'm putting it in logarithmic form, I write the word log, and this is my song. The number under the exponent is the base. The exponent shoots into outer space. The number left over goes in the middle, and that's how you solve the logarithm riddle. The number under the exponent is the base. The exponent shoots into outer space. The number left over goes in the middle, and that's how you solve the logarithm riddle. So, if the song helps, use it. If the song annoyed you greatly, I apologize. And so that is answer choice C. Okay, number 10. Which statement best describes the asymptotic behavior of the graph of log of x? Okay, so let's just look at it. So I'm going to type in log of x and hit graph. Now, you can't see this very well, but what this graph does is it gets really, really close to touching the y-axis down here, but it's never, ever, ever, ever going to touch it. And that's because your x value can't ever be 0 or negative. So that's why it's never going to touch the y-axis, because x cannot be 0, and your x is 0 everywhere right here. So your x can never be 0, so it gets really, 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 really close to touching it. And so what that means is the graph comes really close, but does not cross the line x equals 0. And this is x equals 0. That y-axis, that's its equation, x equals 0. And that's because this right here behind the log can't ever be 0 or negative. So that's why the y-axis is the asymptote, which is that equation. All right, number 11. I'm asked for the inverse. So remember, inverse is when you switch x and y. So there could be a couple ways of doing this. I'm going to try to show you what I think is the easiest. So this point right here, you go right 1 to get there, so the x is 1, and you don't go up or down, so the y is 0. This point, to get there, you go right 1, 2, 3, so your x is 3, and you go up 1, so that's the point 3, 1. Okay, this one over here, I go right 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 2, so that's the point 9, 2. Okay, so the inverse, if it switches the x and the y around, then instead of 1, 0, it'd be 0, 1. Instead of 3, 1, it'd be 1, 3. And instead of 9, 2, it'd be 2, 9. So I need to put these into my y equals and see which one pops up a table that has these numbers. Okay, so let's just try it. So I'm going to put answer choice A in, which is x raised to the third. And I'm going to go to my table. So second graph, and let's see. Do we see 0, 1? No. Answer choice A is out. Okay, let's try B. B is 3 raised to the x. Right? Yeah, 3 raised to the x. Let's go to my table and see if I see 0, 1. Ooh, I do see 0, 1. Do I see 1, 3? Yes, I do. I see 1, 3. And do I see 2, 9? Yes, I do. He's our winner, winner, chicken dinner. So, pretty easy. Hopefully you remember from earlier in the year, the inverse switches the x and y. So just find the points on this graph, switch the x and y around, and then put these in your calculator and see which one has the right table. Not too bad. Okay, next up. Oh, these are my favorite. Unfortunately, I know they're not everybody's favorite, but we have been talking about this business all year long. When does the graph go left? When does it go right? When does it go up? When does it go down? When does it stretch? When does it compress? When does it reflect? But I know it's hard for some of you to remember, so here we go again. All right, so first of all, if it's in the parentheses, it's left or right, and it's always opposite. So a minus in parentheses makes it go to the right. So this is going to go right 2. If it's in the back, it goes up or down, but it does what you would naturally think. So the plus makes it go up, so that goes up 1. So parentheses is left, right, always opposite. Minus is right, plus is left. Back is up or down. Okay, now I know I have a 1/3 in front, but let's just see if we can find the ones that say right 2, up 1. Okay, so right 2, up 1. Okay, he's still in the running. Right 2, up 1. Okay, he's still in the running. Oop, left 2, C's out. Down 2. It's not down 2, it's supposed to be right 2. D's out. Okay, so now we just have to know if it's a stretch or a compression. So this number that's in the front, if it's bigger than 1, it's a stretch. If it's between 0 and 1, 1/2, 1/3, 3/4, 2/3, it's a compression. So it's only a stretch if this is bigger than 1. Okay, so I want it to be a compression, which is answer choice B. Okay, this one. So first let's deal with the parentheses. So parentheses, remember, is left, right, but always opposite. So a minus makes it go to the right. So it's right 3. So let's just look for right 3. 3 to the right, 3 to the right, 3 down. Oh, nope, 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 nope. 3 down. Nope, 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 nope. Okay, so now I just have to know if it's a stretch or a compression. So look at the number in front. Once again, that's not bigger than 1, so this is not a stretch. This is a compression. That number in front is between 0 and 1. It's a compression. Now, if anybody's wondering when it reflects, that's when you have a negative in the front. So if you see a negative in the front, you want to look for reflects over x-axis. So if I saw a negative in front of this, then I'd also look for reflects over x-axis. Okay, those are my two favorite problems ever. All right, number 14. Mike and Marina were working on a math homework together. They were working on solving the equation, blah, 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 blah. Mike says the solution is negative 6, 4, and Marina disagrees and says the solution set is only x equals 4. Which best resolves the disagreement? Okay, so I'm just going to solve it. Now, log is twice on the left side, but I can only work with one log on the left side and one log on the right side, if possible. So I need to condense this. So do you remember when you see addition, what does it tell you to do with these expressions behind the log? You multiply. So I write log base 4, and addition means to multiply. So I'm going to multiply x plus 4 times x minus 2. And then I just recopy equals 2. So when you're condensing logarithms and you see addition, you multiply. If you see subtraction, you divide. Okay, so now I need to multiply these out. So if you guys can do this in your head, that's fantastic. If not, you can just do it off to the side. So I'll do it off to the side for you. X times x is x squared. X times negative 2 is negative 2x. 4 times x is 4x. And 4 times negative 2 is negative 8. Okay, so I'm going to have log base 4. There's nothing to combine the x squared with, so x squared stays x squared. I can combine the negative 2x and 4x in the middle to make a positive 2x. And there's nothing to combine with the negative 8, so he just comes down. And then I just bring down equals 2. Okay, so whenever you just see log once or natural log once, you write it in exponential form. So you start with the base, go around the world, so that's raised to the second power, and that equals x squared plus 2x minus 8. So whenever log is once or natural log is once, you put it in exponential form. The base raised to the power equals this expression. Okay, so what is 4 squared? 16. Okay, let's bring down the other side. Now, this right-hand side is quadratic because the highest exponent's a 2. So whenever you're working with a quadratic, you want one side to say equals 0. So I'm going to make this side a 0 by subtracting 16. So now that's 0. The x squared drops, the plus 2x drops, and then what is negative 8 minus 16? Negative 24. Okay, so now I'm going to factor this. A times c rooftop. So my a is a 1, so a times c is negative 24. And I want the numbers to add to make 2. And do you know what multiplies to make negative 24 and adds to make 2? A positive 6 and a negative 4. Okay, so I get to build my two sets of parentheses. To get x squared, x goes in the front, and these numbers go in the back. Positive 6 minus 4. And I bring down my equal 0. Okay, so solving's easy. If you set x plus 6 equal to 0, you would subtract 6 from both sides, and that would give you negative 6. And if you were to solve x minus 4 equals 0, you would add 4 to both sides, and that would give you x equals 4. Okay, but remember, you can never have a negative number or a 0 behind the log. So I need to go back to the original equation. If I put negative 6, so let's just look at negative 6. If I put negative 6 right there in that x, what's negative 6 plus 4? Negative 2. Can't have a negative back there or a 0. So negative 6 is out. Now, what if I try the 4? If I put 4 up here, 4 plus 4 is 8. Okay, that's good. And if I put 4 here, 4 minus 2 is 2. That's good. Neither of them gave me a 0 or something negative. So 4 is right on. So that means, Marina, you are correct. Okay, I'm going to stop this video here and I'll continue on in a little while. Smiley face.